In today's lecture, we're going to talk through numerical methods for transient problems. We're going to move on from our kind of simpler representation using the Euler technique to more complex methods. These methods that we're going to talk about today are really similar or identical basically to the ones we talked about previously when we went through advanced numerical techniques in transient problems, except that now we're extending these to a 1D situation where previously we just solved them for a 0D problem. So just as a recap of what we went through last time, when you're solving a 1D transient numerical model, the first step is we're going to distribute the nodes spatially throughout the computational domain. We still need our spatial distribution of nodes in this example that we're going through, which is a fin that's activated with some heat transfer at time greater than or equal to 0. The node spacing would be in the x direction. So you see here we have our x direction, so you would have nodes placed in the spatial dimension all the way across. Okay, step 2 is then we carry out an energy balance on each node. Again, exactly the same thing as we've done before. The goal now, instead of where we previously had transient problems where we're just coming up with a state equation that's just a function of time, now we have a state equation vector that has different values for each node. So these different dti values here, these are going to correspond to the ith node in the domain. Okay. Step 3 then is we're going to integrate the state equations forward through time, and that's really what we're talking about today. We did all step 1, 2 previously, and then looked at Euler's technique for step 3. Today we're going to talk through a few different options for step 3 that are maybe a little bit more reliable than Euler's technique. So if we remember where we left, then we said these equations over here describe the state of each node from 1 to n. So we have a state equation that's unique to node 1, a state equation that's unique to node n, and then state equations for all the I nodes in between that. And so these were derived just doing an energy balance on each node. So what we want to do then is to start in these types of problems, it's really helpful to get everything into a function, a single function in MATLAB. And what I mean by that is it's really helpful to have a function that gives you a vector of d temperature, d time, given some moment in time or some particular time step and some particular vector of the current state of temperatures. So we want to have a really convenient way of evaluating those derivatives. So to start off, let's do that. Let's look at this example, transient fin in MATLAB. So you can see here, this is a function that I wrote. This function is returning a vector dt, d temperature, d time, and I'm calling this function transient fin. It's taking in an argument of time, and it's taking in an argument of the current temperature, right? The current time and the current temperature at which we're evaluating our state equation. Right, so it says we're computing a vector. So you can see them, I've entered in the problem information, hopefully the same as what is in the description. And I'm discretizing in here for n spatial nodes. Right, so we have n spatial nodes with dx as the node width. And then we have a vector then that we initialize for our temperature with a function of time, right? So we're initializing a big vector dt dt. We do that with this called, says 0 is n comma 1. That means it's a vector of length n with one column. Okay, so then we go through first. In our first node, we enter our first state equation. This is coming from the energy balance, right? If we look back at our equation here, it's this first node equation. We just start entering that in MATLAB. And note that we're not introducing any time index here, right? This function is only evaluating our state equation at the current time. So we only have space nodes that are present here. Right? So temperature 2 is temperature of node 2, temperature 1 is temperature of node 1, dt dt1 is the rate of temperature with respect to time at node 1, okay, for this given time that we're specifying up here. Okay, so then we loop through the I nodes from 2 to n minus 1 in space with our same state equation. You can note that it's slightly different than this one up here. And then finally, we do our nth node. Okay, and then the function returns, and it's returning this vector dt dt, which is the size of the number of spatial nodes. Okay, so we have that, and that's going to be really useful for us as we're going through and making evaluations in the different methods that we're going to call, right? The methods don't, at least the explicit methods don't really care. You just need to have a function that's evaluating this state equation vector, and then you sort of apply the method on top of that function. Okay, so we'll start off with going through Runga-Kutta. So if you remember, Runga-Kutta is an explicit technique, and the idea is that you're taking a bunch of different estimates of the rate of change at different moments in time and then combining them back together. So if we go through this process, what we're doing is we're saying, I've got some temperature and some time at node j. And I want to take a step forward to temperature and time j plus 1. Right? To do that, I need to have some estimate of the derivative that's involved. And so I'm going to make that estimate based on, in the Runga-Kutta method, 4 different distinct times and distinct or time temperature combinations. Okay? So the first thing is, if I want to step forward, I'm going to start off here at this time j. I'm going to say, I'm going to compute the derivative of temperature with respect to time here, and we'll call that derivative AA. Okay, I'm going to call it AA bar because it's actually a vector, right? We're doing this for every single node, every single spatial node. We're doing this. So now instead of just a single estimate, we have an estimate AA for every single node in space, right? And AA, if we write it, I'm going to do it in a different color here. So if we write it, AA is just the function evaluated at time j and at temperatures j, right? Where the temperatures are t bar, that's our vector of temperatures for all the spatial nodes. Okay, so based on AA, then we get this estimate, which we'll call t hat, and t hat's just kind of our placeholder temperature. T hat is going to be the temperature that we started at, j, right? That's the temperature at each node, plus our vector AA times the time step, delta t, over 2. Okay, so we're using AA to step forward half of the way, delta t over 2. All right, and then the next step is we're going to make another evaluation. So we do another evaluation here, right, at this point in time, and we'll call that BB. So now we're evaluating the derivative at BB, which is halfway through the time step. Okay, so then BB, if we write that out, that is equal to F of, now we're at Tj plus delta T over 2, and we're evaluating at our recently calculated temperatures T hat. Okay, so if we wanted to be, maybe a little bit careful about our notation, I'm going to go back, I'm going to put a bar above F, because really what we're doing is we're evaluating this vector function, right? It's a function applied to a vector, and the function is applied individually to each element in the vector. So that makes it a sort of F bar notation is more appropriate. Okay, so now we have 2 estimates of our derivative. So we will step forward again. So our new step, which we'll again call T hat. Now it's a different T hat, right? It's a different temperature. We're just sort of reusing that same variable name because once you make the evaluation, you just kind of move on. Okay, so our new T hat's going to be T hat at J, which is our current temperature, plus BB vector times delta T over 2. Okay, so what did we do there? We just went back to our initial time over here, and using the derivative that we computed at the midpoint, now we're stepping forward again from, say, here to somewhere over here. Right? So we're again stepping forward halfway through. So then we have a new estimate that we're going to do. At that point, we'll call CC. All right, CC, again, a vector, is going to be equal to the function of Tj plus delta T over 2, evaluated with this new t hat that we calculated from taking the BB step. Right? So CC is now our derivative at that midpoint, but at a different temperature than we were evaluating it before. Okay, then we move on to our new t hat. So we take another step, and we're going to go from t bar j to cc times delta t. Okay, so that's saying now we're going to go back here to the beginning, and using our derivative cc that we just computed, we're going to take a full step over to tj plus 1. Okay, so then that becomes, let's see, at that point, then we make our last evaluation, which is the derivative at the end of the time step dd. And that's going to be f bar tj plus delta t. So that's evaluating now at the end of the time step t hat, which is this most recent t hat that we computed. Okay, so we've done all this stuff. Sorry, we have dd over here, right? So dd is being evaluated at the end. So we have our 4 evaluations of the derivative. And now we need to go back and take our actual step forward in time. So our actual step forward in time is going to be t bar j plus 1. This is the actual step forward for all nodes in space, is equal to tj bar plus some weighting of these different derivatives that we just computed. So the weighting that's commonly accepted for Runga-Kutta is AA bar over 3, or sorry, AA bar over 6, plus BB bar over 3, plus CC bar over 3, plus DD bar over 6, all that times delta T. Okay, so that is fundamentally what we're doing. And just as a, just to be clear about what we're saying we're doing here, we're taking a vector of dt at time, at node 1, dt node 2, dt node 3, dt, and so on, down to dt at node n, dt. Right? And we're saying that's equal to our function of t bar t. So we're computing all these derivatives and then creating a vector where we step forward in time. So let's look at how this actually plays out in MATLAB. So we'll go back to MATLAB, and we're going to look at the example transient fin RK4, which is the Runga-Kutta implementation. And we're doing this based on the function that we just wrote over here, this transient fin. We're going to use this to evaluate our derivatives. And now you can see why it's really helpful to have this function, because we're making this evaluation a bunch of times, and it would be kind of cumbersome to keep track of all those different ones. So we come in here, we discretize in space, discretize in time. Here we're taking 501 steps and simulating for 50 seconds. And then we initialize our temperature array. So our temperature array has to be of size n spatial nodes and m time nodes. And we're doing space nodes first and then time nodes. And then we set our initial condition. So here you can see we're looping through for every single position, space position n. And we're going to set every single space position in the first time step to be t infinity, right? Same thing we've done. So here's our Runga-Kutta. So here's our first evaluation. We're doing it at time j. And we're giving it the temperature at time j. Right? So here, the first time through, when j is equal to 1, we're giving it the temperature vector at j equals 1 and allowing that to be used for the evaluation of the derivative. Right? So we do that, and then we step forward to our new t hat, and then we use our new t hat to evaluate BB at the appropriate time step, CC, and DD. And then in the end, we actually take our time step to our next j plus 1 here, being our current j plus the evaluation of the average derivative times the time step. Okay, so we should be able to do this and run it. And if we run it, hopefully we'll get a plot somewhere. Here we go. So here's our plot, and this looks a lot like the solution that we came up with for the Euler technique, but we are using quite a few less time steps than we had to for the Euler technique.